just saw random variables and their expected values. And I'm assuming that by the time you have reached to this next video, you have at least brushed up these basics and are now comfortable with it. Now, so what is it that we're going to do next? We will try to understand how a probabilistic model provides you an estimate for the unknown. So when you model an unknown, you would also like to ensure that the model provides a good estimate for that unknown. So for instance, in our particular application, this unknown was the answer to a question. And we said that we will model that unknown answer as a random variable with, let's say, a given distribution. And now we would like to understand, once we put such a distribution, what kind of estimates do we have for that unknown? So there are various inequalities in probability that give you such estimates. So one basic estimate that we all know, maybe formally or informally, is that the expected value of the random variable is an estimate for the random variable. That's why it's of course called the expected value of a random variable. Now, we can provide various accuracy guarantees for this estimate. And all these various accuracy guarantees constitute what are sometimes called concentration bounds. So these inequalities, these concentration bounds vary in their degree of complexity. So we'll start with the most basic such inequality, which is called Markov's inequality or Markov inequality. It only applies to non-negative random variables. So here is the statement of Markov inequality. It says that if you have a non-negative random variable x, so it's a non-negative random variable, this is very important here, then probability that x exceeds any number a is less than expected value of x divided by a, and this is true for any non-negative a, okay, in fact any positive a. Alright, so this is just a statement. So before we prove it, let's see what the statement means. Okay, so what this statement means is that we can view so we can recast the statement by choosing a equals to the expected value of x by delta. Okay, so we substitute this as a value for a. So what that statement says is that the probability that a random variable is more than, let's say, 0.1 times its more than 10 times its expected value, that probability is at most 1 by 10. Let's say what the probability that a non-negative random variable exceeds 1,000,000 times the expected value is very small, it's 10 to the power minus 6. Right? So this is how one should read Markov's inequality. It gives a multiplicative accuracy of 1 by probability for expected value. So we can now believe that no random variable can exceed its expected value significantly with a large probability. That's how you can read Markov's inequality. So with this understanding of the statement, let's try to prove Markov's inequality. So this is the first proof I'm doing in this course, and it's a rather simple one. Well, I'll take that back. It's rather simple to follow, but to come up with this proof requires some good idea. Okay, so here is how we prove Markov's inequality. Remember, we have to use the fact that x is non-negative somewhere. So we see the expected value of this random variable x, and we want to bound this probability. So we will try to get this probability out of the expected value. Remember, the expected value of any random variable is x times the density dx. Okay, so this, remember, is the density. And as you recall that this proof, the way we are writing it, it can apply to both continuous and discrete case if we write it equivalently as integral x dpx. Just a notation. This denotes all these things here, and it captures both discrete and continuous. So it's, you just multiply x and multiply it with the probability with which that x appears, and now this is the probability of that infinitesimal small element. That's how you can read this. Okay, so this integral I divide into two ranges. First is a set where x is greater than or equal to a. Okay, so this is one range. And second is the set where x is less than a. That's the second range. So if you look at these two sets, throughout the set, this random variable x is at least a. Okay, so I can bound this quantity here by a. This comes out, this is always greater than a, so this is a integral. Maybe it's a better notation to use. This is that set. Just to describe set to you. Dividing the random variable into two parts. So in this part is always greater than or equal to a. You are left with this, and this is the part where it's greater than a. What about this second part? So this second part is interesting. We would like to claim that this second part is non-negative. Well, x is always non-negative. So this is greater than 0 since x is always greater than or equal to 0. So throughout, wherever we are integrating this, wherever this probability is, this x can only be non-negative. So this entire part must be non-negative. Okay. So if we do that, then this is non-negative. So we can say this is plus 0. That's the bound. So we are left with this. Now this a comes out. And what are you left with? This part is equal to a times the integral of this part. This is just a times the integral of the indicator function that x is greater than a. This is just probability of x greater than or equal to a. Because this was just a constant, integrating a probability over any such constant is just the probability of that event. Okay. And now this is exactly what Markov inequality was claiming if you take a on the other side. That's the proof. So it's very simple, but it requires some thought. Okay, I would urge you to write this proof again, maybe using the summation notation. We have just split the range of summation into two parts. First part where x is greater than a, second part where x is less than a. And when you write that proof, try to follow the proof in this notation as well, so that you become comfortable with this more general notation. Once again, the reason I use this more general notation is so that you can think of the general proof for the discrete case as well as the continuous case. Okay. You can try to understand this proof. What you should now remember completely is this Markov's inequality. I'll use this again and again in this course. It just says that a non-negative random variable exceeds any quantity a with probability at most expected value of x by a. Alternatively, any non-negative random variable exceeds 1 by delta times its expected value with probability at most delta. So it exceeds 1 million times its expected value with probability at most 10 to the power minus 6. So this allows us to at least be convinced about the heuristic that expected value is an estimate for the value of the random variable. In the following sense, it says that with large probability, a non-negative random variable will not exceed its expected value by much. All right. But so this just says it cannot exceed. But how far can it exceed? Can it really fall below expected value? So it cannot exceed by much, but can it fall below? Or is it really close to its expected value? Turns out that the same inequality can be used to get even that kind of estimate. So now, instead of applying the inequality to the random variable x, we apply it to the error x minus expected value of x. In fact, we apply it to the square error. When we do that, we get expected value of x minus, we get that probability that expected value of x minus expected value of x square greater than tau t square. So we get this. How do we get this? We get this by apply Markov inequality to x minus expected value of x square. So same inequality but applied to a slightly different random variable. The error random variable says that the probability with which x minus ex exceeds t is less than equal to expected value of this by t square. So you may now recognize this quantity. This quantity is exactly the variance of the random variable. So this gives us the following bound, which is very useful and sometimes is called Chebyshev's inequality. At least in this course, we'll call this Chebyshev inequality throughout. It says that a random variable x lies between its expected value plus minus some error. This should be plus minus some error. What is that error? That's just square root of variance of the same random variable. So variance of x divided by delta, and it lies in this interval with probability greater than 1 minus delta. And so for instance, if you substitute delta equal to 10 to the power minus 6, it says with probability greater than 1 minus 10 to the power minus 6, the random variable x belongs to expected value of x plus minus 10 to the power 3 variance of x. So just the square root of 1 by delta. So this bound is not tight in the dependence on delta. Sometimes you can, well, very often you can find bounds which have better dependence on delta. But it gives you a very good idea about why the expected value of a random variable is a good estimate for its value. Such bounds are sometimes called confidence bounds. So what we can claim here is that with a confidence of delta, that's the probability, the random variable x lies between its expected value plus minus square root of variance by delta. That's the confidence bound.